Can you hear me and can you see my screen? Thank you. Thank you for the introduction, Ivan. I'm Kunihiko Fujiwara, visiting research fellow at Urban Analytics Lab, NUS. And before starting my own presentation about Microclimate Vision project, let me briefly introduce our lab, Urban Analytics Lab, UAL at National University of Singapore. UAL is part of the National University of Singapore, NUS. NUS is the oldest university in Singapore, with more than 31,000 undergraduates and 18,000 graduate students. And it is ranked 8th globally in the QS university rankings. And our lab belongs to the College of Design and Engineering, which consists of 10 multidisciplinary departments, including architecture, industrial design, biomedical, civil, chemical, and mechanical engineering. And the college is committed to sustainable building design and construction. And one of the buildings, SD4, is recognized as the first newly built net zero energy building in Singapore and Southeast Asia. Additionally, SD4 is the first university building in the world to be well certified gold. And the director of the Urban Analytics Lab is Prof. Philip Lieki. And we have around 15 active members, including today's presenters, Binyu, Xiucheng, and me. Our members have diverse backgrounds, including geography, urban planning, architecture design, landscape design, and microclimate studies. We have conducted research on diverse and interdisciplinary topics. For example, building 3D GIS and urban digital twin, street view imagery, volunteer geographic information, VGI, and spatial data quality. And we are eager to share our achievements through open source software and open datasets. Here are examples of our projects. For example, Global Building Morphology Indicators is a tool to quantitatively evaluate building morphology using the data from OpenStreetMap. And Roofpedia is a project to create a database of building rooftops with solar panels and greenery using a computer vision model and satellite imagery. And Urbanity is a tool to automate the construction of future-rich urban network dataset anywhere. The datasets and code created through these projects are openly available. Specifically, this Urbanity is readily available as a Python package. Through these projects, we have been pursuing a comprehensive approach for urban analytics, which includes not only analytical methods, but also data acquisition, data quality, and data harmonization. Okay, that's all for the brief introduction of UAL. And now let's move on to my presentation. And I will share our work, Microclimate Vision, multimodal prediction of climatic parameters using street level and satellite imagery. Okay. Before starting the explanation of the project, let me introduce briefly about myself. I have been working as a researcher at Takenaka Corporation, which is a construction company in Japan, and as a PhD researcher at Tokyo Institute of Technology, and as a visiting research fellow at UAL. Over the past about 10 years of research, I have consistently worked on urban microclimate. Some of my work has been on field measurements, and some on numerical simulation, and some on optimization of tree arrangements for heat mitigation, and some on optimization of building design. And I would also like to explain the general background regarding climate change and microclimate, because some of you might not be familiar with microclimate. As everyone knows, air temperature is rising globally and is expected to continue rising in the future due to climate change. This figure from IPCC's synthesis report shows that heat risks for human health is also increasing. I guess some of you understand this change from your own experience. To address these increasing heat risks, we need to consider microclimate and heat adaptation strategies. Microclimate refers to the local climate conditions influenced by urban morphological features such as building, trees, water bodies, and soil. Well, changing the global climate takes very long time. We can change this microclimate and mitigate heat risks by modifying such urban environment, by adding trees, shading, and so on. To strategically plan heat adaptation, we need to start by assessing the current condition of microclimate at the high resolution. So now let's move on to the main part, Microclimate Vision project, done by these team members at UAL. First, I want you all to think about this question. Which place do you think is hotter? Place A and place B within an urban block, let's say in Singapore. You need to answer this only by these street level imagery information. I bet most of you chose A based on your experience. You might expect that A is hotter because of the openness and lack of shade to protect sunlight exposure. You might think that B should be cooler because the surrounding trees that cool the atmosphere through transpiration. And these assumptions are generally correct and supported by numerous previous studies using field measurements and numerical simulations. And this shows that we can estimate microclimate condition to some extent just from these visual information. Then we hypothesized that it is not only possible for human, but also for computer, especially, more specifically for computer vision to estimate microclimate from imagery inputs. However, at the time of this project conception, there was no computer vision-based method for microclimate assessment. Meanwhile, two main existing methods for microclimate assessments, field measurements and numerical simulations, both have scalability issues. For measurements, dense networks of weather stations require significant budget. And for numerical simulations, it requires intensive manual labor to prepare detailed 3D city models. Therefore, we aimed to develop a computer vision-based prediction model as a potential alternative to the existing methods. And this is the task of our prediction model. The model predicts microclimate, including air temperature, relative humidity, wind speed, and also global horizontal irradiance of target location using microclimate data and of reference location and imagery inputs like street level imagery and satellite imagery of both reference location and target location. And by the way, this global horizontal irradiance is the energy of solar irradiance absorbed by a horizontal surface. The model was designed to extract feature difference between reference and target location. And using this information, convert the reference microclimate data to target microclimate prediction. We incorporated both street level and satellite imagery to provide the model with more comprehensive information on the surrounding urban morphological features. And this is the framework of the entire project. We collected microclimate data and street level and satellite imagery, and then trained and validated the prediction model within the collected dataset. And using the trained model, we demonstrated high resolution mapping for microclimate as the example use case. And our study area was located in the NUS campus, where we collected microclimate data using 12 fixed weather stations. Here are some examples of collected microclimate data. We can see that the values vary substantially among weather stations. For example, the maximum difference reaches around 4 degrees for air temperature, and about 10% for relative humidity, and 2 meters per second for wind speed, and 800 watt per square meter for global horizontal irradiance. This indicates that the variation in surrounding morphological features significantly impact microclimate variations. And additionally, we collected street level imagery using a GoPro Max camera and satellite imagery using the Mapbox API. For street level imagery, we use panoramic imagery. We use panoramic images to capture urban morphological features from every angle. And here are some examples of the collected imagery for the weather stations. And using the collected dataset, we trained and validated our prediction model. This is the architecture of the proposed model. Our model consists of 5 branches. LSTM branch for input reference microclimate, and 4 ResNet 18 branches for street level and satellite imagery of reference and target locations. And the model concatenates output feature vectors from these branches, and MLP processes it and outputs the final target microclimate prediction. And the LSTM branch can process time series microclimate data with timestamp of the target time and preceding 24 hours, allowing the model to incorporate the history of reference microclimate. Additionally, this architecture outputs 1 microclimate parameter. So we trained 4 individual models for the 4 parameters. This approach ensures that each model has its own optimal weights to capture features in imagery inputs that significantly influence each parameter. And this is the resulting performance of the trained model. Focusing on RMSE, the model achieved 0.95 degree for air temperature and 2.57% for relative humidity, 0.31 meter per second for wind speed, and 225 watt per square meter for GHI, global horizontal irradiance. We also compared accuracy with 4 different scenarios with different input types. And across all the parameters and error metrics, scenarios that use imagery inputs outperformed those without imagery inputs. This indicates the contribution of imagery inputs to the higher accuracy. And also, across most of the parameters and error metrics, the scenario with all input types performed the best, highlighting the contribution of comprehensive inputs. And focusing on R square, air temperature and relative humidity achieved better scores, whereas wind speed and GHI, especially GHI, showed weaker accuracies. However, the overall results indicate sufficient accuracy for some implementations, such as assessing the spatial variations of microclimate. Here are scatter density plots comparing the prediction results and measured ground truth data. The plots for air temperature and relative humidity show significant positive correlation like this. And the plots for wind speed and global horizontal irradiance show weaker correlations, corresponding to the worse accuracy compared to air temperature and relative humidity. However, these plots still show some correlation, some positive correlation. We attributed this relatively poor accuracies of wind speed and GHI prediction to the strong locality of wind and solar radiation. Especially for solar radiation, even small clouds or a few leaves in tree could significantly change the values, making it challenging for the model to accurately predict the values. However, I want to emphasize again that the overall results indicate sufficient accuracy for some implementations, such as assessing the spatial variations of microclimate. Therefore, we demonstrated high-resolution maps as a use case of our model. We first collected geotagged street level and satellite imagery at about 5,000 locations along the main walking paths in the study area using a GoPro Max camera and Mapbox API. We then created high-resolution maps using the collected imagery inputs and the trained prediction model. Here are the maps for air temperature and relative humidity. The street level image of a location with a higher air temperature show less vegetation and relatively high openness. This corresponds to the previous studies that reported higher air temperature due to sunlight exposure and impervious ground surfaces without evapotranspiration. And a place with higher relative humidity shows a large amount of vegetation and less openness, which aligns with previous findings of higher humidity from transpiration. And here are maps for wind speed and global horizontal irradiance. Location with higher values are featured by significant openness for both wind speed and global horizontal irradiance. This also corresponds to previous studies that observed higher values in places without windshields and shading. And the model can also be used to create time series maps. Here are maps for air temperature from 9 a.m. to 2 p.m. on a target date. These maps enable us to capture hot spots and cool spots that varies throughout the day. We can use these high-resolution maps for example, issuing hotspot alerts and cool spot recommendation, and also optimizing working route choice to mitigate heat stress. And moving on to limitation and direction for future work, the model trained in this study can only be applied to the study area. So we believe that it is important to expand the dataset and generalize the model's predictability for other areas with diverse morphological features, like high-rise buildings, water bodies, different plant species, and so on. And additionally, we haven't yet quantitatively analyzed the correlation between morphological features and prediction results. Therefore, it's important to analyze correlation between the pixel ratio of elements, such as vegetation, and parameters like air temperature. So, a paper regarding the Microclimate Vision project has been published from the journal Sustainable City and Society. And the scripts of the prediction model are openly available on GitHub. So please check them out if you want to dive deeper. And feel free to reach out to me using the email address provided in the paper. And in today's discussion session, I'd like to discuss, for example, further details for the study, if you are interested in, and your ideas for potential application of or variation of our method, or potential future collaboration between us. That's all for my presentation. Thank you for listening.
Yeah, thank you very much, Dr. Fujiwara. Okay, we will leave the questions to the last. So maybe Ms. Binyu, can you share your screen?
Yeah, sure. Let me share my screen. So everyone can see my screen now? All right. So please wait a second. So good morning and good evening, everyone. Today I'm going to share our latest research, which is predicting building characteristics at urban scale using graph neural networks and street-level context. So this paper is co-authored with Peng Yuan, Nicola, and also Philip. So before I start my sharing, so let me briefly introduce myself. My name is Binyu Lei, and I'm a final year PhD candidate at Urban Analytics Lab, supervised by Philip Bielski. And I received my master degree in urban planning from University of Melbourne. My research interest includes urban informatics, human-centric urban digital twins, and also urban technology. At the meantime, I'm also a member of 30 Information Management Domain Working Group at OGC. So as we all know, building information actually plays a role in many domains. Therefore, geospatial building data can facilitate a diversity of use cases, such as simulating energy use for urban sustainability, analyzing urban climate in the microenvironment, and also to integrate different urban forms and to help monitor socioeconomic growth. However, the availability of building information actually varies across cities. So for example, in City A, the number of building stories may be partially available, while in City B, the type of buildings is incomplete, in fact. So to conduct the prediction of different building attributes, we design a workflow containing 3 main steps. So the first step is to collect building information and also the street-level urban features. So the innovation in this paper is to leverage the spatial relationships between buildings and also their surrounding urban objects. So for example, you can see from the screenshot of the satellite image. So this is a building and it is surrounded by a car park and also a number of trees. So therefore, we are intended to capture the urban objects within different circular buffers of 50, 200, and 500 meters around buildings of interest to kind of shape the spatial connectivity between the buildings and also their surroundings. And the second step is to use the graph-seq algorithm for constructing spatial connectivity between buildings and also aggregating features and finally forming an inductive graph representation. So the first part includes to aggregate street-level urban features as the node features to each building, which is considered as a node in our framework. And then we construct the spatial connectivity among buildings, which are represented the edges in the framework. And then we have our graph inductive representation, and then we can use this kind of model to do the downstream predictions. So the last step is to implement the framework to conduct our tasks, including regression model and also the classification model. So in more detail, the model is graph-based and also it is designed bifurcated. And so it contains 2 separate tasks. So the first one is the regression task, which is for learning continuous target variables such as the building height and also the number of floors. And the second task is the classification task, which is for predicting distinct class labels such as building types and the details of roof and also the building construction materials. And for these 2 kinds of tasks, we leverage a variety of metrics to evaluate its performance. So to make our methodology more globally relevant, we choose 3 global cities as our study areas, which are Boston, Melbourne, and also Helsinki. So different cities contain different richness of building information. So for example, Boston only include available building characteristics, for example, the number of floors and also the building type, while the city of Helsinki actually covers more diverse building information. So they also provide building age and building material. So this is the results of our model performance. And through including a variety of evaluation metrics, for example, RMSE, MAE, median relative error, we observe that our model actually outperforms random forest, which is our baseline model in this work. And so the middle figure is the realization of our predictions in the city of Boston. So you can see from the right column, this is actually the prediction error in Boston. So we found an average of 81% of buildings in 3 cities have less than 1-story prediction error. And also the prediction of building type achieves an average of 88% accuracy across these 3 cities. So further, we include some scenarios to investigate the impact of varying local data availability on model performance. So we designed 3 types of scenarios, which are cities with 10%, 30%, and 50% of building data availability relative to the total building data set. And through the results and also the evaluation, we found MODI's training data often suffices for acceptable results. And to better illustrate the usability of our method or this framework, we use the estimated number of stories to generate a 3D city model in LOD1 in the city of Boston. We store the kind of generated dataset in CityJSON format and do the visualization on Ninja platform, which is a web-based platform. So when you click each building, and you can find the building ID, number of story, and also the building type, and also our predicted stories and predicted type, and also the estimated height. We just extrude the buildings based on the building footprint and also the estimated height into the 3D city model. And to quickly conclude this sharing, so we demonstrate for the first time how spatially explicit graph neural networks can help predict different building attributes and also to improve other standard machine learning approaches, such as random forest, which is used as the base model in our framework, and which can only indirectly capture the spatial relationships between buildings and their surrounding urban environments. And we also find the value of street level context is actually strongly predictive, especially in the absence of any information about the building itself. We also think the development method, so the graph-based model can, and also associated with the findings of this research, can be useful for the researchers and practitioners to mitigate the data gap in building information. And also we hope this kind of framework can support a number of downstream studies. And our paper has already published in computers, environment, and urban systems. And we also make our code open source on our GitHub, and this is a link. So if you are interested in this work and also want to know more details, you can check it out. And also we welcome you to visit our GitHub repository to replicate our work and also do the model training and prediction on your own side. And this is my contact, and I'm happy to have like any further discussions and chats like in the breakout rooms. And thank you.
Thank you very much, Binyu. Yeah, so now we have the last speaker, Xiucheng. Thank you very much. Can you share your screen?
Yeah, can you see my screen? Yeah, okay. Yeah, hi everyone. Good morning and good evening. And my name is Xiucheng. I'm also one of the lab members from UAL in NUS. Today, I'm going to give you an introduction of my recent research on evaluating human perception of building exterior using street view imagery. Unlike previous research, my topic would be more related to human itself, like more related to psychological analysis on like how people perceive building facade in a city scale. So yeah, before I start, I give a brief introduction of myself. And my name is Xiucheng Liang, and I graduated from Shenzhen University before. My subject is more related to urban planning and design. And later on, I pursued my master degree in NUS and start to transfer into urban analytics with Philip. And now I'm pursuing my PhD since last year. So now I'm a second year PhD student in the lab. So yeah, going back to my research, and my research is more related to urban perception, which is a very popular topic recently, because there are a lot of street view imagery available, and also there is a very popular data set released by MIT Sensible Lab and which is widely used in recent research to evaluate human perception on the streetscape in the cities. However, it's kind of a bit challenged and haven't been really discussed, like how can we also evaluate like building facade design, because this is also a very important aspect as architecture design studies, and which is also very important, like how this kind of architecture design can actually affect like this kind of streetscape perception in the cities. So yeah, this kind of urban perception research are also very famous, popular, because like it's kind of related to how people really feel on the built environment, and also can also affect like people's restoration and also their stress recovery of built environment. Lastly, they might also, this kind of research can also contribute to like how human mobility and also how their travel behavior will be affected in the visual experiences. So yeah, learning from the framework of the place post datasets, which is more related to streetscape research. We also conducted research on the building facade. Firstly, we have street view imagery, and we extract and detect the building from the street view imagery into an individual building imagery, and then we set up a criteria regarding 6 different dimensional perceptual indicators, and we conduct a survey from around 500 participants to evaluate building facade imagery based on their perceptions. So this kind of perception score, then later on we'll train the model and predict more building imagery in a city scale, and we try to generalize this idea into 3 cities: Singapore, San Francisco, and Amsterdam. And also we have a session to discuss like how this kind of building design might affect the streetscape perception, which is from the data set of place spots. So yeah, to give you more detail, when we conduct a survey among 500 participants and on around 1,200 building imagery. So we have a survey, like ask the people to compare the building imagery and based on their understanding of the built environment regarding 6 aspects. Basically, it's more like ask you like which building imagery in the survey you found is more complex, more original, and maybe more order or more boring. The participant would choose one of the options based on their feelings. And after that, we did a survey, and we have a data set for training the model. So each dimension, as I mentioned, like 6 dimensional indicators we can use to train the model and predict the image on a larger scale, and more image will be influenced by this kind of building perception model. And we evaluate the score for around 250,000 images in the cities. So this is the result we collect from the survey. So basically you can see like each building will have a certain kinds of score for certain dimension of perceptual indicators. So let's say the first one will be perceived as more ordered, and also the last one will be more kind of original and also very complex from their understanding. So this is the data set we have, and we try to use it and predict the more building imagery in a larger scale, so that we can compare like how this kind of characteristic of building distributes or locates in the cities. So this is the overall prediction result distribution in 3 different cities. And then you can easily evaluate like some cities, like let's say the building in Singapore would be more ordered, because like we have a lot of unified HDB, like public housing. So this would perceived as more ordered, and we have more buildings are located in this kind of characteristic. And also in Singapore, they will have like more modern building because like the city is like fully developed and fully urbanized. So there are a lot of modern building in the city, while San Francisco and Amsterdam will have a lot of historical building from this perspective. So yeah, this is some of the results generated from the model. Like some building, like on the right-hand side, they will be perceived as more ordered, and there are some less ordered building can be also be evaluated based on the model. So this is another examples. Like more building will have a like higher original score. They will perceive as giving a higher score on original, and there were some simple design and like some buildings will have a lower original score based on their design. So this is kind of a concept, and we also did a activation map on this kind of building prediction result, because like we want to see whether the models like fully understand like which part of the image like make the model to have certain kinds of decisions. So yeah, this is a general idea to see like which area of the imagery. Let's say the first one would be like less compressed. The model will focus on certain kinds of less compressed area of the building, and also they will focus on some horizontal line and within the image to give the building image a certain kinds of score on like whether it's high ordered building or less ordered building. So we also managed to like map this kind, aggregate this kind of score in a city scale and within different kinds of cities. So they have a general impression is like in the city center, they will have more compressed buildings amongst these three cities. And as I mentioned, like Singapore have a lot of public housing, and which is you kind of unified and have a lot of horizontal line. So such kind of area will perceive as a very like highly ordered area with building design. So yeah, this is kind of the concept. We also kind of map whether certain kinds of area, the building design in certain kinds of area is boring or pleasing. Yeah, based on this kind of method. And so and then we also try to compare certain kinds of regression relationship, like correlation relationship among the building perception score, and also like whether it's like with their functions of the area, also the building age of the area, and lastly also the distance to city center. So we calculate certain kinds of characteristics within the three cities and showcase how the building design are differentiated from the cities. Lastly, we also apply propensity score matching and to see how certain kinds of building perception would affect the streetscape, like overall streetscape perception. So there are some kinds of indicators have been identified in the past, like which is more important. It's important they have certain kinds of influence on the streetscape perception, which are building and sky, the proportion of the sky, the proportion of the road, and proportion of the vegetations. Like let's say higher vegetation, stands have a higher vegetation, people usually will perceive have more beautiful or maybe some like less boring in some cases. So the low level features, ages, and both of the street view imagery will also affect people's perception. So our first idea is try to control the image, like which having similar image features, and then compare the building within those imagery and see how the building design will affect the human perceptions of the streetscape. So yeah, this is the propensity score, the matching result. So we will have, this is some of the examples, like we will have one group having a low building capacity, and one group have a treatment group have a higher building capacity. So So we will compare the streetscape perception score based on this pair of imagery, and this imagery based on we collect the image feature and apply the propensity score matching to make sure they have certain kinds of similarity in the building features. So yeah, this is some other result. So on the left-hand side, the group will have a low building capacity. On the right-hand side, we have a high building capacity. And then we calculate the score, like how this kind of building will affect the streetscape perceptions. So yeah, this is the final result. Like we apply this kind of method, and then we quantify the certain kinds of effects like on the streetscape perception. So this is the effect of the treatment effect of streetscape perception. Let's say there are some example. Let's say if a place with a more pressing building design within the streetscape, the people will tend to perceive this kind of place would be more will be safer. And also, if they have more ordered or compact building within the streetscape, the people will tend to like perceive this place safer. So yeah, there's some ideas like if the place have like less pressing building and the building design is like not that historical, and they will perceive this place will be more boring. So this is kind of the way to show how can we manage or monitor this kind of building design within a streetscape to improve certain kinds of perception of the overall streetscape. So yeah, lastly, and also after like this kind of work and with Binyu, the presenter before, and we also apply this kind of data set into measuring the human perception and integrate it into the 3D city model and as a application of urban digital twin. So basically, we measure the streetscape perception of certain kinds of building and assign this kind of perceptual score into the 3D building model as an extension of the CDGML model. And after in the platform, you can easily click on each building and you can identify certain kinds of score of human perception. So based on these integrations, we can easily filter out certain kinds of building. Let's say they both have the objective value and subjective score. So let's say we want to find buildings have a score, pressing score, like looks more pressing, like larger than 5. And also we can identify buildings like having a construct before 1950. So we can easily identify these kind of buildings and within the urban environment. So this can lead to a more human-centric direction of the further applications across different kinds of disciplinaries. So this is kind of the concept, how we, or use case, how we apply this kind of data to evaluate the human perception on the building. So yeah, and so these two work have been published online, and one is in building and environment, another is in a conference paper. Please feel free to look into more detail, and if you are interested, and I'm also welcome to discuss later on in the discussion session. And also, if you are interested, you have some interesting idea and on how we can evaluate this kind of building facade and extract the information from building from imagery. And we are also welcome to discuss and collaborate in the future. So yeah, thank you so much for your time. And yeah, this is my linking QR code. And if you are also want to have a further discussion, you can also add me in the linking. Yeah, thank you.
Okay, thank you very much for all the presenters and the presentations and the time to showcase the research projects that is going on related to urban sustainability and AI. So now I'm going to open the floor for 5 to 10 minutes before we go into the breakout room. But also depends on like how active the conversation is. If you have any questions that you would like to ask before entering the breakout room, please do so. Or you can leave a comment in the chat so I can ask the speakers on your behalf as well. Yeah, because there are like okay. Miguel, do you have a
I
hey,
have a
hi.
question. Hi, I have a question from the first presenter, if possible, for microclimate mapping. Can you hear me?
Yes.
Hi.
Yeah.
A very good work. I realized you have used those models, like mostly ResNet models. Have you had the idea like using foundation models, like because now the new wave, there are foundation models available. Have you thought about using them, or is it possible to use those models for your work or similar works?
Thank you for your question. For that project, we didn't consider about usage of foundation model as a part of our prediction model. But yeah, I think it's a very interesting idea, and I think we can include foundation model as part of our prediction model, and that may improve the prediction accuracy. Yeah, so, but I've never tried this kind of idea, so maybe as a next step, we will try, or we will consider about this idea further. Thank you.
Thank you.
And Miguel?
Yeah, if you don't mind, I really have a question, I guess, for the 3 speakers, no? Because of course, what I can see is that for the moment, you essentially tested all your methods and the information you want to extract, from the street imagery.